Right now, the microchip inside the device you're using to listen to this is operating like fractions of a degree away from physically melting itself into slag.
Which is terrifying when you think about it.
Right. It totally is.
Yeah.
And the only thing keeping it alive isn't the tiny fan, and it's not the heatsink either. It is an invisible mathematical fence.
Yeah, a strict algebraic boundary.
Exactly. A boundary dictating exactly how much power can flow to the CPU before the physical architecture, literally destroys itself.
It is a phenomenal high-wire act. I mean, we spend so much time thinking about computing power and engineering as this race to just be the fastest or the most powerful. But in reality, high-level engineering is entirely about mastering limitations.
Which brings us to the mission for today's deep dive. Whether you are prepping to optimize a massive cloud deployment, designing hardware, or, you just have an insatiable curiosity about the invisible logic governing our most complex systems.
We are looking at how to absolutely maximize outcomes under incredibly strict limitations.
Right. And we have a stack of notes here to help us do that. Excerpts from an engineering course titled Day 31 Linear Programming, Engineering Applications.
And right at the top of these notes, there's this really fascinating mandate. It notes that we are technically past the original, quote, July 15th finish line for this curriculum.
Yeah, they mentioned that right up front.
Right, but the directive is to push forward anyway, because in practical engineering, crossing an arbitrary calendar date means nothing if you haven't locked down the structural mathematical logic. The goal is finishing strong.
I love that framing. Like, the calendar's a fake constraint, but the physics, those are real constraints. So, okay, let's unpack this.
Let's do it.
Before we get into launching rockets or managing thermals on a microchip, you need to understand the skeletal structure of this logic. The notes anchor everything in Chapter 12, specifically sections 12.1 and 12.2.
The foundational stuff.
Yeah. And I want to be clear for everyone listening, programming here doesn't mean like writing JavaScript. We're talking about formulating problem spaces mathematically.
Exactly. Linear programming, or LP, is an algebraic system composed of three structural parts. And the first is your objective function, which is usually denoted as z.
Right, the letter Z.
Right. This is your ultimate goal expressed as a linear equation, like z equals a times x plus b times y. And you strictly want to either maximize this function, like driving up profit or yield or engine thrust.
Or minimize it, right?
Yes, exactly. Minimize things like latency or material cost or weight.
But the real world doesn't just let Z go to infinity, unfortunately, which introduces the second component, the constraints.
The fun part.
Right, the things holding the system back. These are the hard physical limitations modeled algebraically as linear inequalities. So instead of a flat equal sign, we're looking at less than or equal to scenarios.
Right, like c times x plus d times y is less than or equal to e.
Because, you only have so much battery wattage or so much physical cubic volume inside a rocket fairing. You can't just wish for more space.
And when you graph those constraints on a coordinate plane, those intersecting inequality lines enclose a specific bounded area.
And that's our third component, right? The feasible region.
Exactly, the feasible region. Every single point inside that overlapping area represents a mathematically possible combination of your variables where all the inequalities are true.
But we don't just want a possible solution.
Yeah.
We want the absolute optimum. We want the best possible setup.
Which brings us to the fundamental theorem of linear programming, the golden rule of this whole system.
Lay it on us.
The optimal solution will always occur at one of the corner points, the vertices, of that enclosed polygon.
So if I can just jump in and use an analogy here to visualize this. Imagine the feasible region is this weirdly shaped, fenced-in backyard. The fence represents all your constraints.
Okay, I'm picturing it.
And the optimal vertex is basically the furthest specific corner of that yard where a dog can reach the absolute longest stick.
That's a great way to put it.
You push it all the way to the corner where two fences meet.
What's fascinating here is how this exact geometric principle maps directly to concrete physical reality. We are looking at spaces where mistakes cost millions of dollars.
So let's transition from that abstract fenced-in yard on a graph and see how these algebraic variables map to actual physical systems.
Yeah.
The notes outline three specific domains, starting with aerospace engineering.
Right, designing a satellite launch profile. In this scenario, we have two variables we need to lock in.
Our X and Y.
Exactly. Our X variable is payload mass, the actual weight of the satellite, and our Y variable is additional propellant volume, the fuel.
And our objective function here, our Z, is maximizing the orbital delta V.
Right, the total velocity change capability. We need to maximize the maneuverability the payload has once it actually gets to orbit.
But obviously, you can't just pack infinite fuel and infinite satellites. You've got physical limitations.
Major limitations. We have two massive constraints here. First, the physical cubic volume inside the payload fairing.
The actual space inside the nose cone.
Yes. And second, the thrust-to-weight lifting capacity of the booster stage. The rocket engines can only lift so much mass against Earth's gravity.
Right, so if you try to maximize delta V by just dumping way more fuel into the equation, you quickly slam into that thrust-to-weight constraint. The rocket gets too heavy to launch.
And if you try to maximize the payload size by building a massive satellite, you hit the cubic volume constraint, it physically won't fit in the fairing.
So the optimal vertex, that exact corner point we talked about, is finding the precise ratio that maximizes delta V without snapping the fairing or making the rocket too heavy.
It's pure geometric optimization, finding that perfect balance point.
And if you don't hit that vertex, you're just leaving orbital performance on the table.
Yeah.
But, okay, it's one thing to balance constraints when you're dealing with a massive aerospace launch.
Sure.
The notes move us from the massive scale of rockets to the microscopic scale of electronics engineering, specifically power allocation on a system on chip, or SO.
Where the margins of error are just non-existent. On a modern SO, your variables are the processing units. So your X is your standard CPU, and your Y is a dedicated neural processing unit.
An NPU, right, for AI tasks.
Exactly. And the objective function here is to maximize floating point operations per second teraflop PS. You want the highest possible computational throughput.
We want the chip chewing through data, but the constraints are brutal. First, we have a strict 15-watt power budget limit from the battery.
Right. X plus Y cannot exceed 15 watts.
And the second constraint is the thermal dissipation capacity, the TDP,
Yeah.
basically the cooling limit.
If you push too much voltage, you generate too much heat, and the chip dies. So the optimal vertex is finding that perfect power split, say, exactly 9 watts to the CPU and 6 watts to the NPU.
Okay, wait, hold on. I have to push back on this for a second.
Oh, sure. What's up?
We're talking about linear programming, right?
Right.
Which uses linear equations, straight lines. But thermodynamics, like the heat generated when you push current through silicon, that is not strictly linear. Heat generation curves exponentially.
Yeah.
So what actually happens when you push past that thermal constraint vertex? Is it just a math error? Or does the silicon literally melt? Aren't we using the wrong math?
That is a brilliant question. You are entirely correct that thermal runaway is nonlinear. The physics get very scary very fast.
Right.
So in practice, what engineers do is they use piecewise linear approximation. They essentially take that terrifying exponential heat curve and they draw a very conservative, straight, linear boundary just inside the safe zone.
Oh, wow. So they fake a straight line before it curves.
Exactly. The linear constraint is drawn tight enough that the system will mathematically stop allocating power well before the chip reaches that physical inflection point where the heat spikes.
That is wild. So defining those constraints accurately in the math is literally a matter of physical survival for the hardware. If your straight line is off, the chip melts.
Yep. It's why this math is so critical.
Okay, so we've explored physical volume in aerospace and physical heat in electronics. But the discussion in the notes then shifts to the invisible digital infrastructure, the virtual realm.
Right, software and cloud computing. And the geometry remains exactly the same, but the physical limitations become completely virtual.
We are looking at operating a Kubernetes cluster serving a web application. So our variables here are the pods.
Yes. Your X variable is your database pods, and your Y variable is your web server pods.
And our objective function, our Z, is maximizing concurrent user requests. We want to handle as much traffic as possible.
But again, we hit constraints. The physical memory of the server rack your RAM limit, and the available virtual CPUs your CPU cores limit.
Because database pods eat up RAM, and web server pods eat up CPUs, right?
Precisely. And the optimal vertex in the cloud means calculating the exact allocation ratio that utilizes 100% of the hardware.
But without crossing the line.
Exactly. Crucially, staying within those constraints at that specific vertex prevents catastrophic out-of-memory crashes, while ensuring maximum user capacity.
Here's where it gets really interesting. Think about the through line we just drew for the listener.
It's universal.
It totally is.
Yeah.
The exact same algebraic formula that dictates rocket fuel ratios in space is the same math that allocates SOSC wattage to stop a chip from melting.
Mm-hmm.
And it's the exact same math that unites the cloud architect managing a Kubernetes cluster to avoid an OM crash. It's just The math is universal.
It really is the underlying syntax of optimization. But, understanding the universal theory across these three domains is powerful, sure.
We need to make it practical.
Right. To provide immediate value, you need to know how to actually compute this in the real world, because
Yeah.
you're not doing this on graph paper.
Right. The notes move to practical code implementation.
Yeah.
The directive here is setting up these linear inequalities and running them through a specific Python library, scip.optimize.linprog.
Yes, linprog. It's a standard tool, but there's a massive trap here to watch for. The notes urgently point out a crucial technical gotcha. That specific Python tool, scip.optimize.linprog, is strictly designed for minimization.
Wait, really?
Yeah, it is hard-coded to find the lowest possible value.
But every single example we just talked about, delta V, teraflop PS, user requests, those were all maximization problems.
Exactly. So if you just feed your parameters into that tool, it will optimize for the worst possible outcome. It will find the absolute lowest performance for you.
Okay, so to explain how to work around this trap, let me supply an analogy. It's like imagine you have a GPS that only knows how to find the lowest valley in a landscape.
Okay.
But you want to maximize your outcome. You want to find the highest mountain peak. To trick the GPS, you basically have to hold the map upside down.
That's a perfect way to visualize it. Mathematically, you have to invert the signs of your objective function coefficients.
The positive becomes a negative.
Exactly. You artificially make your goal negative. The algorithm aggressively minimizes that negative value, driving it as low as it can go in the math.
And then when you flip the result back to reality, boom, you found your highest mountain peak.
Exactly. It's an elegant hack for a rigid tool constraint. And visualizing that math is actually the final piece of the source material.
Right, the interactive element of learning linear programming. The notes talk about adjusting constraint bounds in real time.
Yeah, using sliders to physically warp the feasible region on a graph. If we connect this to the bigger picture, this interactive shifting is so important.
Because it shows the constraints moving.
Yes. It helps you realize that constraints aren't just static roadblocks. They dynamically dictate where your optimal success can live. If you add more RAM to a server, the boundary line physically moves, and your optimal vertex shifts instantly.
So what does this all mean for you listening right now? You might not be launching rockets or coding in Python today.
But you deal with constraints.
Exactly. You can view your own workflows, your meetings, or your personal projects as LP problems. You just have to identify your ultimate Z function. What are you trying to maximize?
And map out your actual constraints. Budget, time, bandwidth.
Right. Once you map those inequalities, you find your perfect vertex. You stop guessing and you start optimizing.
It's a mindset shift.
It really is.
Yeah.
So to recap this journey, we started past the July 15th finish line with Chapter 12 Algebra. We flew through aerospace payload ratios. We managed melting 15-watt silicon chips.
Yeah, balance Kubernetes pods to avoid OM crashes.
And we dodged the minimization trap in Python's scip.optimize.linprog by holding the map upside down. We covered a lot of ground.
We really did. It's a robust framework.
But I want to leave you with a final, provocative thought to mull over on your own. Something that builds on today's lesson.
Oh, I know where this is going.
All the examples we discussed today use just two variables, right? An X and a Y.
Yeah.
And that results in a neat 2D shape on a graph with easy-to-spot corners.
Something we can easily draw and see.
Right. But what happens in a modern engineering problem, or like an AI model that has 1,000 or 1,000,000 variables?
The geometry completely explodes.
Exactly. The human brain completely fails to visualize a million-dimensional polygon. We just can't picture it. Yet, and this is the crazy part, this exact same mathematical structural logic still holds true.
It scales perfectly.
It flawlessly finds that one invisible, hyperdimensional corner of optimization, even when we can't see it. The math just works.
It's incredible to think about.
It really is. So keep seeking out those optimal vertices in your own lives, whatever your variables might be. Thanks for joining us, and we'll catch you on the next Deep Dive.